Hi everyone, and welcome back to your channel Fundamentals of Engineering with Farhad. Mechanics of Materials. We want to calculate the reaction for this 1 degree indeterminate beam, which is consists of a fixed end at A and a ruler supported B, and also distributed load of W, constant loading of W at the top. We want to calculate reaction at A, reaction at B, and also the angle of rotation at B. So if you remember, we already solved this problem with two different approaches. We are going to solve this problem with four separate approaches. Like the first approach is like solution 1, determination of elastic curve from moment. Solution 2, consider moment at A as a redundant. Solution 3, which is the topic of today's problem, is consider of R sub B as a redundant, and finally solving with Castigliano's theorem. So if you remember in solution 1, which I will provide you with the link to those video for some of you want to review them, determination of elastic curve from moment. If we cut the beam through by a length of x somewhere in the middle and develop the moment equation and integrate it twice, we can get the delta or delta function. And meanwhile, the calculation of R sub A and R sub B and also theta at B. Solution 2 is considering the moment at A as a redundant. If we remove this moment at the fixed end A, this beam, this 1 degree indeterminate beam, transform to two simple supported beam, one with the effect of moment, the other with the effect of the distributed loading. And today's talk is about the considering the reaction at B as a redundant. So if we remove this support and solve the problem, and finally we will solve it with the Castigliano's theorem. So in our case, we can dissect our problem into two beam by removing the support at B. We will have like a cantilever beam with the constant loading of W plus a cantilever beam, and just apply the effect of reaction at B. By superposition of these two effects, we can have like the problem gets solved. So as soon as we have like conversion of our original beam to dissect it to these two determinate beam, the cantilever with the distributed load, it just moves downward. This is the delta or tangential deviation of V with respect to A for the first one, and the other one, R sub B, just pushes the beam upward a little bit. And if we just call it the tangential deviation of B with respect to A induced by loading, and this is TB with respect to A induced by reaction at B. Then superposition of these two, it just gives us the tangential deviation of B with respect to A. And as you can see here, the superposition of these two is the key to solve the problem for third solution. And as you can see here, there is no upward and downward movement for point B because of the reaction in original beam. So that the tangential B with respect to A total is equal to 0. And that's the key to solving this problem. Let's head on. For the first part of the problem, just cantilever beam with a distributed load of W. If we just draw the shear and moment diagram, be careful, we want to have it like M over EI. This is the shear diagram, and then if you draw the moment diagram, then you can easily get the amount of the moment and then tangential deviation of B with respect to A, which is this downward movement, that's equal to area under M over EI, this area, times X bar, which is the centroid of the M over EI, calculated from the centroid to the free end B. So if this is a constant loading, the shear is 1 first degree, and this parabolic spandrel is the second degree, so the area is 1/3 of WL squared over 2EI times the length, then times X bar is 3/4 of L. It just gives us T tangential deviation of B with respect to A for the first part is WL to the fourth over EI. If you remember, we can also calculate the theta of B, and if you pay a closer look, you can easily see at A there is no theta because that's fixed, and it just gives us theta at A is equal to 0. So theta at B is the area under M over EI. That's 1/3 of WL squared over 2EI times L, which gives us WL cubed over 6EI. This is the first part. If we do the same for the second part, the cantilever beam with the effect of R sub B in upward direction. So this is the deformed beam. And if you have it like the moment M over EI, draw it, it just gives us the tangential deviation of B with respect to A, B with respect to A for this part which is induced by R sub B, that's equal to the area of this triangle, that's a half of L times RB over L over EI. So the moment created here is just the force times the length, so RB times L, and then divided by EI, that's M over EI, and then times 2/3 of L, which is the distance of the centroid of our triangle to free end B. And it just gives us R tangential deviation of B with respect to A created by reaction at B is RBL cubed over 3EI. And theta at B is also the area under this triangle. RB is still unknown. We'll solve it in next step. Now the superposition of these two parts comes to play, and by having that, it just says tangential deviation of B with respect to A total is equal to the first part plus the second part, TB with over A from loading plus tangential deviation of B from a R sub B, and definitely it's equal to 0 as you remember because there is no movement for B. That's why we consider it here. Then it just says if we replace, and be careful about the direction because the first beam is moves downward and the other one it just moves upward. So this negative it just comes from the downward. You can use negative for either of them, but it needs to be consistent. So we choose the negative for downward, so that's a negative WL to the force over 8 EI plus RBL cubed over 3 EI is equal to 0. It just gives us RB is 3 over 8 W. My bad. That's 3 over 8. So that's 3 over 8 WL. Then if we have it like there, if we have like RB is 3 over 8 WL, then summation of forces should cancel out the total loading. That's 5, that gives us RA is 5 over 8 WL, and that that also makes sense because the bigger chunk of the force is handled by reaction at A. That's why RA is bigger than RB. And for calculation of theta, we have two parts, so we can call it theta B of first diagram, that's theta B, that's the area under this diagram, we already calculate that, and also the theta B2, that's the area of the second triangle, and RB we already calculated to RB is equal to, my bad, that's 3 over 8. If you replace that in the equation, it just gives you the R theta B is equal to a negative or 3 over 16 WL cubed over EI, and theta b total is a negative WL cubed over 48 EI. So we already have our RA, RB, and also the angle of rotation at B, which is WL cubed over 48 EI. Thank you. We'll solve it with the Castigliano's method in next video.